Welcome back to our Chem 152 video series. In this video, we'll use a reaction table to find the equilibrium constant if we don't know it. In part 1 of our reaction table series, we worked on a problem where we were given the equilibrium constant, but were asked to find the equilibrium concentrations of all the species. This problem is slightly different. This time, we're given the starting concentrations and one equilibrium concentration, and our goal this time is to get the equilibrium constant. Remember that anytime you do a reaction table problem, there are three pieces of information involved: the initial concentrations, the change, and the equilibrium constant itself. In this problem, the starting concentrations are provided, so we have the initial. We'll be able to find the change based on the equilibrium concentrations. But what we don't know here is the equilibrium constant. That's going to be our goal for this question. Let's begin constructing the table. We write down our species, N2 plus O2 yields 2NO, all gases. My initial concentration of N2 is 0.0362 molarity. Concentration of O2 is 0.0090 molarity. And notice that we do not have a starting concentration for NO. We have the equilibrium concentration of NO. Therefore, we must be very careful here. We're going to put this equilibrium concentration of NO not on the initial line, but on the equilibrium line. Once again, the way that we know that is because it says equilibrium concentration of NO, not initial concentration. This will go on the equilibrium line here. Now, since we don't have a starting concentration for NO, we can safely assume that is 0. Now, notice we have not filled in the change yet, but we can see that we know the initial concentration for NO and the final equilibrium concentration for NO. The change for NO will be the equilibrium concentration minus the initial concentration. Our equilibrium concentration is 3.6 E-4. The initial concentration was 0, and so if we subtract, we get 3.6 times 10 to the negative 4 for our change of NO. With this information, we can find the change for the other two species as well. To find the change for the other two species, we can use stoichiometry. Our change for NO was 3.6 times 10 to the negative 4 molarity. We will multiply by a fraction to get out of NO and get into the species we want. Let's start by doing N2. And we'll write down the coefficients on this fraction. We have 1 of N2 and 2 of NO. And to show that N2 is a reactant and it'll be used up, we'll say -1. In order to make anything on the right, we must use up the things on the left. If we do the multiplication, 3.6 times 10 to the negative 4, times -1/2, we will get -1.8 times 10 to the negative 4. Now we look at O2. We notice that O2 has the same coefficient as N2, and therefore we can expect the change to be the same. Therefore, because we know N2 is 1.8 E-4, we know that O2 must be the same, -1.8 E-4. To find the equilibrium concentrations, we will subtract using a calculator. Our first subtraction will give us 0.03602 molarity. This is our concentration of N2 at equilibrium. Our second subtraction will give us 0.00882 molarity. This is going to be our equilibrium concentration of O2. Now we find the equilibrium constant, which was the initial goal of this question. Remember that K is products divided by reactants. Our product is going to be the NO. We're going to raise that to the second power because there is a 2 coefficient in front of it. On the bottom of this fraction, we will have N2 multiplied by O2. Now we input the molarities from the equilibrium line of our reaction table. Therefore, we will have 3.6 times 10 to the negative fourth raised to the second power divided by 0.03602 multiplied by 0.00882. You may wish to add a second set of parentheses in the denominator because we have multiple terms. Then we use a calculator to divide. On the top, we will get 1.296 times 10 to the negative 7th. On the bottom, we multiply. We'll get 3.177 times 10 to the negative 4th power. And when we divide these terms, we get 4.1 times 10 to the negative 4th power for our K value. And so now, by using initial data and equilibrium data, we have deduced the equilibrium constant of this reaction, even though we didn't know it when we started. Thank you for watching, and we'll see you again soon.